All right, so we are starting sequences and series. Completely different brain concepts than what we've been in. So I know for those of you who really like structure and numbers and everything where it's at, it's like, oh, we've gone from equations and graphing and curved lines that we've been doing for about 3 months, right? And now it's like, what? We're doing a whole nother section. Okay, so there are some ways I'm going to show today that these tie into a little bit of old information that we have, but for the most part, sequence and series are a different brain section. So if you're ready for a break, this is a good break for us to have, right? Last week we did an intro to sequences and series, talked about what the vocabulary of a sequences and a series means. I wanted to get that out there, have your brain start working on it, and hopefully you worked a little bit on the homework problems. If you're like, I didn't understand the homework at all, great. Do it this week. You can add it on like it wasn't a big deal. So if you didn't have it turned in for this week, I just didn't grade it. It wasn't a big deal. You can do it for next week. If there's parts you're like, I got it, but I want to redo some more, that's the whole point. We're going to go over it all today. Last week I wanted to get the information out there. We have such a limited time that sometimes it's nice to just kind of already have it in your brain of this is what it looks like. Okay? So sequences and series as we move through. I just wrote this out, so again, you guys have full access to these notes and you can go back. But sequence and series, and so these are some common things between them, and you can see a lot of it is very similar. So sequence is simply a list of numbers. A sequence is going to have a comma between all your numbers. A series is when that same exact list gets added up. Those are the only two differences between them. So for both, you can have finite and infinite. Finite means it has an ending, like maybe it's only 10 terms. Infinite means it goes on forever. We can have finite and infinite of both. They both have to have a pattern. They both can be arithmetic or arithmetic, it depends on who you're listening to, or geometric. So remember, arithmetic, reading, writing arithmetic. Arithmetic refers to addition, subtraction. Okay? Geometric is going to be multiplication or division. And I think I talk about why a little bit later. But just remember that that's the difference. One deals with addition and subtraction, one deals with multiplication or a division type thing. So we're going to have a ratio thing. When it comes to series, we are going to have this special notation. This is the term sigma. Okay, you can think sigma means sum. There's an S. So you're going to have sigma notation. You will also have it written as the sum of n numbers, like that. Sometimes I just write an E, sometimes I write the little things on it. Depends on how fast I'm writing. Okay? So that's where we're headed. So again, sequences, we're going to start with sequence. We have to understand our sequence first before we can actually add it up. Okay? So when it comes to sequences, they have to have a pattern. So in yellow I have up here. If you have a list of numbers that does not have a pattern, it is not a sequence. So if I just write 1, 5, 14, 21, 22, 27, this is not a sequence. It does not have a pattern. Okay? If I wrote 1, 2, 4, 7, I'm having to think on the fly, 11, you might say, oh, this one increases by 1, this increases by 2, this increases by 3, that increases by 4. It has a pattern of what it's increasing, not a sequence. The pattern must be constant between all of your values. Okay? So yes, what you're jumping could be considered a sequence, but the numbers themselves are not a sequence. Okay? So if it does not have a pattern, it is not a sequence. Okay? Like I said, the arithmetic sequence means that we have some sort of pattern that is found by addition and subtraction. A geometric sequence is found through multiplication and division, and that is because Geometry deals with shapes, right? So in arithmetic, we're dealing with a number line, correct? With addition and subtraction. Geometry deals with shapes. When I have shapes, what am I doing to find area? We're multiplying, right? So when we think of geometry, the whole purpose of geometry is to find area of circles or squares or cones or cubes or whatever else with that. And so geometry means that we have to multiply. So that helps remember that geometric sequences deal with multiplication with some ratio, okay? Two new variables we're going to need to know, D and R. Okay, these are important variables. D for an arithmetic sequence is a common difference. Isn't that nice? Difference. What is the term that we've used maybe since 3rd grade for difference? What is the math? Subtraction, right? And so that means it also could be addition. So when we have a difference, we are getting there either by addition or subtraction. For geometric, we have this new term called R. It stands for a common ratio. What does ratio mean? Remember when we talked about rational numbers? A ratio simply means a fraction. Right? We can make any number into a fraction by putting it over the number 1. Right? Fractions are found through division or by multiplying, maybe by an inverse or something. So when we have ratios, ratios are found through division and multiplication. Okay? So those are our 2 new terms that we need to know, our new variables for that. Okay? Sometimes you already know in advance, they'll tell you this is your common difference or this is your common ratio and this is what you're starting. Sometimes we know that up front. Sometimes we don't know that up front and we have to figure that out. And that was a lot of homework this last week. Some of it, the first part of it, they gave you the formula. They gave you the difference. You were just having to fill it in. The other part, they didn't give it to you. So there are a couple of different ways that we can figure that out, okay? The important thing to learn through all of this that may be the most confusing part, if you don't quite understand this, is that sequences are written in relation to 2 different things. And I'm going to tie that back into a linear equation, okay? So we are super used to x and y. Everyone agree, like, if I gave you x and y values, you would be able to graph those on a coordinate plane? Okay, so sequences are these lists of numbers in relation to their term placement. So they are called terms, okay? And this is their placement. Okay. Their placement is your n value, if you keep saying n. This is going to be your n value. If we were comparing this to x and y, our placement is our x value. So if I had a graph and I was going to graph all of these, I would say, let's do this one. We'll do that sequence. At 1, I'm at 1. At 2, I'm at 3. At 3, I'm at 5. At 5, I'm at 7. Or at 4, I'm at 7. At 5, I'm at 9. Okay. Do you see how that's how we would graph it? Our term placement, our n's, will always be in order. They will not be skipped. They will always be 1, 2, 3, 4, 5. They will be integers in counting order beginning at the number 1. Right? So this is basically like your x value. Your y value, your term value is similar to your y value. It's what you get when you plug in your equation. So if I have a sub n equals 2n minus 1, which is what this sequence is, what if I rewrote it in something that we're familiar with? What if I rewrote this as f of x equals 2x minus 1? Could you guys solve this for the different values? This f of x equals 2x minus 1, and I said when x is 1, when x is 2, when x is 3, when x is 4, when x is 5. Okay? So the top one looks real familiar when we've seen it. We would also be able to say when f of x equals 2x minus 1 that this is what type of equation if I graphed it? Linear, I heard it, linear, because my x only has an exponent of 1. This is a linear equation. When I graphed it, did it look like a line? Yeah, this looks like a line, straight through. Okay. So when we are looking at it, remember that even though they're placed one on top of the other and it's like a sequence, it is in relationship to the same thing that we've done before as functions. It's not completely brand new. So for some, it's easier to think of it in like the x and y terms. For some, it's easier to say, hey, this is a sequence value. So I just want you guys to see that there is a relationship here. What's neat is that because this sequence graphs like a line, what is our main line equation? What is our parent function for a line? Y equal, well, that's the pure line, the slope of any line. Mx plus b. Okay, does that look like this? Yeah, it does. Okay, and so what we're going to be able to see is that as we start writing for our series and our equations, that this y equals mx plus b format can really help us when we don't know maybe what the sequence formula looks like and we're having to ask through that way, okay? So this is how it's all related. What we're taking is we're saying when n, or when our x value is 1, what is y? What is our term value? Right? Okay, so on another thing that we're learning is just these new written variables or notations. So when we have a sub n, it is a subscript. The n value is telling you your term placement, where in this sequence. So if I did a sub 4, I am looking for the 4th value of the sequence. So I would go 1, 2, 3, 4. So a sub 4 equals 7. Okay? So if we went back, it would also be like saying f of x. So when x is 4, what do I have? My y is equal to 7. Any questions on this notation? Okay. So our subscripts tell us not the value, but the term location. Our subscripts are telling us that x location of where we're going to find it along the list. Okay? So a couple of helpful steps for writing sequence if they don't give this to you in the first place. These are some steps that we can use. One, we're going to look at our numbers and say, do I see if anything is in common between them? My first step is always going to say, do they have the same thing added or subtracted? So we always start there because that's the easiest one to start, okay? So from this, I would say, how do I get from the first one to the second one? I call this jumps. And so that is the terminology that you're going to constantly hear me say, is how many jumps are we making? Okay? So if I go from 1 to 3, I can jump there by adding 2. Okay? Well, remember, a sequence has to have a repeatable pattern. So I'm going to try that a couple of different times. If I go from 5 to 7, oh, I added 2. From 7 to 9, I added 2. Oh, okay, from 3 to 5, I added 2. So I can confidently say that this is a sequence, and my jumps are from adding 2 to it, okay? If it wasn't like that, say it was 1, let me do this one, 1, 2, 4, 8, 16. Okay, when I added 1, but adding 1 doesn't work for 4, so I know addition and subtraction doesn't work. So then I'm going to go to multiplication. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. Okay, that's consistent. I could say this is through multiplication on times 2. So this sequence would be a geometric sequence because it uses multiplication. The top sequence is an arithmetic sequence because it uses addition. Questions? The multiplication, remember, this could be add or subtract. It could also be division, like we could have done it times 1/2. So it can be a fraction, which is basically the same as dividing by 2. So we're going to look for those different ones, and then we're going to look at it and say, how can I rewrite this number on top in relation to my number on the bottom? And that's where like the f of x comes in. It's like, if I plug in 2, how do I make a value for 3? And we're going to come up and show, I'm going to show you just a little bit how to actually make that and show you that it really turns into y equals mx plus b. So it makes it a lot easier for it. Now, here's a special rule, and unfortunately one of your homework problems had it and I didn't make a note on it. Sometimes a sequence can have 2 different formulas that govern it, okay? It can have a formula that governs the positive, or the, like maybe the odd values, and it could have a formula that governs the even values of it. So you would notice from 1 to 3 to 5, it stays with this certain pattern. From 2 to 4 to 6 to 8, it stays with this certain pattern. So sometimes they can have multiple expressions that can define it. And one of yours, like right at the beginning. I hate when they do that, and they like throw a really hard one right in there, and you're like, I'm just trying to figure it out. Okay, so that's our sequences. Okay, so then how does it relate? And we're going to practice and go some others. How does this whole thing relate, now that we know what we're talking about when we have a list of sequences, to a series? Well, as soon as I take the same exact list of numbers and I put addition signs between them instead of commas, I've now changed this list of numbers from a sequence into a series. Okay, that's all it means. And so since it now is a series, it has a different term, which is our summation term. And it is our instruction booklet. Okay? These are instructions. And so it's important to know how to read the instruction guide to know what they're asking you to do. Okay? So when you see the sigma, it will say sum. Like I said, you could also, they may also say like the sum of n terms in that. Okay? And it gives you lots of information. There's lots of information. I wrote it up here. I'm not sure how good it is showing up. So specifically the sum means to add. You're going to have different numbers. You're going to have a number on the bottom and maybe a number on the top. The value that they place here will be a whole host of values. Typically you're going to see I. This does not mean imaginary numbers. Just because we're working with n, you'll see me write it a lot as n. It could be a, it could be x. It's basically just saying f of whatever that value is, okay? The terms on the bottom and the top, so we have a lower limit and we have an upper limit. These numbers relate to the location of the value in your sequence. So if I say from 1 to 5, that means take every number from space 1 to space 5. If I said from 3 to 5, I'm only going to take the values from space 3 to space 5. Does that make sense? I could say from 2 to 4, and I would only be add up 3, 5, and 7. So our lower limit and our upper limit are the numbers of our term location and telling us which of the top, which of the y values, which of our term values that we're actually going to add together. So you might not be adding all of them together. You might just be taking a segment of them. Any questions about these notation spots? No? Okay. So now that we know what it says, you will have some sort of expression. So we'll write 2n minus 1. So that will be our expression. This expression tells us what the numbers are. It gives us our values. So I could say, what is this value when n is 2? 2 times 2 is 4 minus 1, so I've got 3. And I know I have to go from 2 to 4. So I'd have 2, and then I'd have 3. 2 times 3 is 6 minus 1 is 5. 2 times 4 is 8 minus 1 is 7. Okay? This is our expression that we are plugging our x values into, if we're going to relate it like that. It is telling us how to get the actual numbers. Okay? This is convenient when we only have 3 numbers. It's not super convenient when we have 50 numbers that we have to add up. Okay? But do we understand how to read our sigma notation? Yes. Okay? Okay. So we are going to practice on this one. If we said to write this in summation notation. So if you are given a list of values, so that one is 5, 10, 15, all the way to 100. Okay. When I am writing, my personal preference is to draw my little lines and write my term values underneath them so that I can figure out what it is. I'm not given a term value for that 100. I was just given the numbers, and I'm like, I'm not really sure how I'm getting there, okay? So then, if you're not given anything, we have to find our sequence expression. So if this is my x value, how do I go from here to there? How did I get from 1 to 5? How do I go from 2 to 10? What do I see that these have in common as well? What are we doing? We're adding 5, right? We're adding 5 for all of our jumps. Okay, so 5 is going to be a number involved in it. Can I go from 1 to 5 through something? Times 5? How do I go from 2 to 10? Times 5. How do I go from 3 to 15? Times 5. Okay, so I've got a 5. Super consistent with that. So if my value, if I replace this 1 with an x, let's do n, since I've been using n values. If I replace that with n, okay, I need to take my n and multiply it times 5 to get my number on top. So I could say f of n is equal to 5n, right? So when it's 1, when n is 1, my value is 5. When n is 2, my value is 10. Does that make sense? Everyone agree here? So what would it be to be 100? So I know my top is 100. It means 5 times whatever my n value is. So n would have to be 20. now I have my lower limit. My lower limit is 1, and now I have my upper limit. My upper limit is 20. So we're going to put our lower limit down here as 1. We figured out what our upper limit was. Our upper limit is now 20. And then we just write our expression that told us how to get that value in front of it. Any questions about that? Okay. I have, that's not the one I wanted to do. Let's look at a couple of these for sequences. Okay, so if we have a sequence, let's do 2, -4, 8, 10, 14. All right. So in this, oh, that's supposed to be -10, isn't it?
Oh,
There we go. Okay. So there's a couple of different things. Oh, I don't want to do that one first. We're going to leave that one up. Let's do this one. Okay. So if we have that as our sequence, and we know it's going to go on, let's write an expression for telling us how to get the top number in relation to our bottom number. Okay. So if our bottom number is, this is location 1, 2, 3, 4. Okay. Is there something in common to get there? We know that we're not.
I'm multiplying by 10.
Yeah, we're multiplying by 10. Okay, but we can't do that. So if we're multiplying, the multiplication has to be in relation to our term location, right? These in values. So when we start dealing with multiplication, we see that something is a constant like that, we're going to have to drop it down and go, how did I get from here to there? Okay, so we're dealing with that ratio. Look, okay? So could I just say 2 times 10? I could, and that wouldn't work there. It would work for the first one, but not for the second one. So I can't multiply times 10. Is there a way that we can rewrite our values so that it has something of our bottom in common? See, what if I rewrote this as 10 times 1, 10 to the 1, sorry, 10 to the 2, 10 cubed. Okay. Now they all have the same base, right? How could I rewrite 1? 10 to the 0. Nice. Okay. Now, can I go from my in value, my term location, and write something in relationship to the top? Do you see anything with our numbers? Now we have a constant of 10.
10
right?
to the n minus
10
1.
to the n minus 1. So I can go from 1 to here if I say it's 10 to the n minus 1. 1 minus 1 gets me 0. I can go from 2 to 10 to the first by saying my n is 2. So this is the part where your brain has to start thinking through and say, I have to use this number on the bottom as my n value. So somewhere in this equation, I've got to plug in 2 to end up on the top. Somewhere in this equation, I've got to plug in 3 to be able to get my number on the top. Is that making sense? Okay. So sometimes we've got to look at it and, it's kind of Sherlock Holmesy. go, how can I use my number on the bottom to get what I get on the top? Okay, this is one I like. Okay, as we start doing sequences, you will start seeing patterns, and you'll get used to like, oh, I know how to make that happen. Okay, so first and foremost in this, we're gonna write our term locations. So this is 1, 2, 3, and 4. We've got to use those terms somehow. How can I go from 1 to 5? How can I go from 2 to 10? How can I go from 3 to 15? Because if I'm looking at it, I don't have the same jumps, right? Because this is minus 15, or sorry, plus 15, and then minus 25. So I can't do anything addition or subtraction to go. So I know it's maybe got to be multiplication or division. So is there anything in common between maybe our x and our y values here?
5.
5. So I know that I can take whatever my number is on the bottom, so my n value on the bottom, and I can multiply it times 5 to get up here. 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15, 5 times 4 is 20. Okay, so that gets us our base number. The problem lies in these negatives. Okay, what do we notice? What do we assume the next number is going to be?
Negative 25.
Negative 25, positive 30, negative 35. Okay? This is a pattern that is very common. When you have alternating negative numbers, we can get an alternating negative number using an exponent. Correct? So if I did negative 1 to the 1, what do I get? Negative 1. But if I do negative 1 squared, I get 1. Negative 1 cubed, negative 1. Negative 1 to the 4th, 1. Okay, I can get alternating negative numbers by taking a negative number to an exponent, because as I change it, it goes back and forth. Does that make sense? Okay, so if I'm starting with negative, how did I get a negative in the first place? I started with 1. Oh, 1 matches 1. So we can write in front of this negative 1 to the n. This negative 1 to the n whole section, all it does, since it's 1, does 1 really change? Does 1 ever change your number? No, it doesn't change your number at all. All it does is affect the sign. So when it's 1, it's negative. When it's 2, it's positive. When it's 3, it's negative. When it's 4, it's positive. Do you see that pattern here? So when you have alternating negative, positive numbers, this negative 1 to your term value, your n value, is going to be at play in here. Now, what if it started with a positive? What if it went positive, negative, positive, negative, positive, negative? How could we change this so that we're still alternating, but we get it positive in the first place? Positive means that my exponent has to be even. So how do I take my exponent and make it even? Add 1. Perfect. So we could say n plus 1. And that would start it out being positive. We clear on that one? So then we would have positive. Then my next one, 2 plus 1 is 3. So then we would be back to an odd one. And an odd term gives us a negative value. And then, so we have just shifted where we want our exponent so that it could adjust where our positive and negatives lie. Does that make sense? Questions? Take notes. Okay. So then let's look at this top one here. Okay. So if we're going to do it in relation to our terms, this is term 1, 2, 3, 4, 5. Okay. Do we see a pattern if we're jumping, this is one of the ones that has a different one. Did we see a pattern if we were jumping back and forth from 2 to -4? No. -4 to 8. I don't see a pattern there. I do see a pattern, and so then can we find a pattern that goes multiplication or division? Well, 2 times 2 would give me 4, 1 times 2 gives me 2, but then 3 times 2 does not give me 8. So now my multiplication doesn't work either. So in this one, we are jumping by odd numbers. Okay, so from 2 to 8 is 6, from 8 to 14 is 6. Okay, and then let's look at these other ones. From -4 to -10, so it's 6, but it's negative, right? So we have some that are positive. It's jumping by positive whenever it's the odd values. It's jumping by negatives when it's the even values. So it's jumping by the same amounts. They're just one set's positive, one set's negative. So in this case, we have 2 different values. So how can I go from 1, if I know I've got a 6, so this is where it's always, I'm like, we're going to have something involved in there, okay? So how are we getting from 1 to 2? How are we going from 3 to 8? How would we go from 5 to 14? So we're only looking at those ones that we're addressing with. Okay? And the formula for that is if I do 3 times 3, gives me 9, but I'm 1 less than it, 8. 5 times 3 gives me 15, I'm 1 less than it. 1 times 3 gives me 3, I'm 1 less than it. So for those odd numbers, we have 3 times n minus 1 was our first one. So that was one on your homework. That was pretty difficult. Okay. And so then we can adjust that and say, it's probably going to be something very similar to this for the bottom ones. Okay, so if I do maybe a -3, right? -3 times n gives me -6. How do I get back to a -4? We're going to add 2. -3 times 4 gives me -12. I'm going to add 2 and get back to 10. So typically, I will say that typically when you have pairs, you're going to have a very similar value that's going to be with your n values. Okay? Do I have any more practice on those? Okay. Let's look at this one. 14, 11, 8, 5, 2. Is that a sequence?
Yeah, it's done -3.
Yes, it is. It is -3. Okay? What if we had Is that a sequence? Okay. Why do you think it's a sequence?
Is that a comma or a 1?
They're commas. Doing a sequence between there.
It's just getting multiplied by 2. The numerators.
The numerators are multiplied by 2. Okay. If we're looking at, yes, so that would be a arithmetic or a geometric? Geometric. Okay. If you were asked, is this an arithmetic sequence? What would you say? No. Okay. So understand the difference if they're asking arithmetic, even if you're like, oh, but it is a sequence, but it's not arithmetic.
Oh, did you say arithmetic?
No, I just asked if it was a sequence.
Oh, okay.
Yeah, so we can look at them and say, yes, this one was arithmetic, this one is geometric. We'll look across those, right? And the more we do them, the easier finding the actual value becomes. We're going to work through some more. Hey, where's my clicker? Oh, thank you, sir. Okay. All right, so last week we addressed a little bit of things about actually summing up the numbers. And I used the little rainbows for it. Okay. So there are 3 very special types of series. Now that we've moved, when we have a sequence, so very specific sequences, we can find those series through 3 different formulas that we can memorize. They're really common sense. 2 of them are like absolute common sense. The other one you just have to memorize for it. But if I have a whole bunch of 1s added up, so my summation notation says the sum of this lower limit to the upper limit of the number 1. So all I'm doing is, basically it's saying, no matter what the term location, my value is going to be 1 in it. If I add up a whole bunch of 1s, I'm just going to get the number of what I'm adding up. If I add up 4 1s, I'm going to have 4. If I add up 20 1s, I'm going to have 20. Does that make sense? Common sense. So this rule says that when you are adding up, when you have the sum of a whole bunch of 1s, your answer is simply the upper limit. Right? So it's written in this way. When your lower limit is 1, and the important part about all of these is that you're actually starting at the first value. When your lower limit is 1, and you're going to some other number, then your answer is going to be that upper limit. So if I'm going from 1 to 100 of the number 1, when I add them all up, I'm going to get 100. Does that make sense? Okay, that one's a pretty common sense one. Okay, the second one is a series of positive integers. That means anything that's positive, and we start at the number 1. Okay, so this specific one, and we're going to be able to expand this out and show how it's actually the same. It is the same equation for our generic equation. But specifically, if we are starting where our very first term value, so in the a sub 1 place, we have the value 1, then our formula says that all we have to do is add them up. It's written in this way, that we have half the number of terms times our number plus 1. Okay, and the easiest way to think about this is, I actually try not to memorize this thing. What we're doing is we're making that rainbow. We're saying we are averaging the first and the last one, and we have that many of the averages. So if I have 1, 2, 3, 4, 5, 6, we showed this on the board last week. If I did 1 plus 6, I have 7. 2 plus 5, I have 7. 3 plus 4, I have 7. So as we start at the beginning and we go to the end and we pair them up, they will equal the exact same number every single time. And that's because this is a sequence. So when I go from 1 to 2, it's the same amount as subtracting from 6 to 5. So those cancel out. Does that make sense? That's why they're always going to be the same, because whatever you have jumped on the front end, you're undoing that jump on the back end, and they're canceling each other out. So as we are adding up any positive numbers that start at the number 1, what are we doing? We're taking our very last term and we're adding 1 to it, because we started at 1. Right? That's why it's adding 1. So I'm taking 6, my last term, my upper limit, and I'm adding 1 to it, and I'm getting 7. And how many 7s do I have? 3. I have, because since I'm pairing them, the amount of pairs that I have is only half of the values that I had. Right? And so if I have 6 terms, 1, 2, 3, 4, 5, 6 actual spaces, then I'm going to have 3 pairs. I'm going to have 3 pairs of 7. That makes sense? And we're going to be able to expand this this equation out to work for all arithmetic sequences or that are written as a series. Okay? So this is one that we're going to do on our own. So we can work this out on paper. So here is our generic term. What does this say? Let's walk through what this is saying. I'm going to sum up terms from 1 to 9. So how many values am I going to have? 9. I've got 9 terms. So if I wrote it out, I would have 9 blanks. Right? The values in those blanks are found by saying 2n minus 1. So the value, if I've got 2n minus 1, we already know that this is our odd sequence, right? So for this first one, I've got 1, 3, 5, 7, 9, 11, 13, 15. Okay? So it always helps me to kind of write out a few of them in the first place. But what are the most important values that I need to know when I'm summing it up? I need to know the first value. Do all the middle values really matter? What do I need to know? The last value. Because we are adding the first plus the last, and we know that everything else in the middle has to be the same number, right? So when we're doing this, I'm going to find my first value, and I'm going to plug in 2 to the 1 minus 1, and get 1. And then I'm going to plug in my upper limit, 9. So when we plug in 9, we get 2 times 9 is 18 minus 1, we get 17. So we know that our pairs are going to pair up to be 18, right? First value plus our last value. So now I know what my pair is going to be. Now how many pairs am I going to have? How many terms do I have? I've got 9 terms, and I'm going to have half that amount. So when we have an even amount of terms, they all pair up evenly, correct? When we have an odd amount of terms, we have that one guy right in the middle left over. What do we notice that the guy in the middle left over is in relation to our total?
Half.
It's exactly half. It will always end up being exactly half. I like to keep it written as a ratio here. So I've got 18. I've got when it pairs up, it gives me 18, and I have 4.5 of those. So if I added all of these up, it would be 18 divided by 2, 81. 9 times 9 is 81. Any questions? So what we did is we took our formula and it said a to the n plus 1. So here's my a to the n. When it says a to the n plus 1, what is my n value now? This 9. All right? So a to the 9, a sub 9, what was in a sub 9? 17. 17 plus 1 gave me 18. So that's where I get 18 for this first part. And then I have half my number of terms. So when we are writing it, it has our n value we're ultimately looking at is that upper limit. We're going to plug that upper limit in there. Okay. Another special one is called the series of squares. So as we notice, our terms are the squared values. So this is 1, 2, 3, 4, 5, 6. So all we're doing is squaring our x values. Okay. How would we write that one? We could say that it's the summation of 1 to, on that one we'll say 1 to 6 of n squared. I'm taking my location value, my x location, my n term, and I'm squaring it to get my y, or my term value, okay? So we're gonna write this out and we're gonna see, does our pairing trick work? No. Our pairing trick does not work for squares. So this has a very special formula. You can memorize it. Formulas like this I'd probably just put on your test for you to be able to use. When it's squared, we basically take the n number of terms times the next number up. So here we had 6 terms, so it's going to be 6 times 7, and then we use 2n plus 1. Okay? And then the whole thing is always going to be divided by 6. So in this case, the only thing that you'll need to know is how to actually use this formula. So the n value, if you were plugging in an n value, would you plug in the lower limit or would you plug in the upper limit? The upper limit. Good job. You're going to always plug in the upper limit. So if it's from 1 to 9, we're going to have 9 times 10 times 2 times 9, 18 plus 1, 19, all divided by 6, if your upper limit was 9. Okay, so it's just a matter of using that formula. And they have, if you want to read through how it actually did it, they show that in your book too. You don't have time today, okay? So for this one, I have these just written out with actual numbers in them. So if I am adding up 42 ones, my answer is going to be 42. Excellent. If I am adding up 1 to 5, I started at 1, I'm ending at 5. What does its pair make? 6. So I've got 6, and how many of those pairs do I have?
5.
I have half of my 5, right? Because I paired them up. So my total pairs are going to be 5 halves. Right?
Do we leave it as 5 halves or change it to 2 and 1 half?
If you're multiplying and simplifying it out, it's much easier to leave it like this. Because, right, I can say 2 goes into 6 3 times and my answer is 15. If I write 6 times 2.5, you know, use your calculator if you don't, unless you do decimals in your head, great. If I write 6 times 2 and 1 half, I'm still got to simplify it out that way. So until you're fully simplified, I leave it as a fraction, even if it's an improper fraction. Okay. And then from 1 to 18 of just a value I, whenever it's written where it's just your term, that means all you're doing is plugging the term in. So how would I write that out if I was actually writing them as a sequence? What does that look like? Right? That looks like 1, 2, 3, 4, 5. Right? So I'm going to go from 1 to 18. Here's my lower limit of 1. My upper limit is 18. In this case, I wrote it as an n. In this case, I wrote it as an I. These are the same equation. They just have a different variable. Like I said, sometimes they use different variables, and that's fine. So same thing. Our lower limit is 1. Our upper limit is 18. When I pair those together, I get 19. And how many pairs do I have?
9.
Half of 18. So I have 9 pairs. So it's going to be 19 times 9. Gives me 171. Okay, so let's look at a couple of these. Is the top one an arithmetic sequence? What do we think? This top one. Is it a sequence?
No.
I don't think so.
Oh yeah, plus 4.
Plus 4. If I add 4 to each number, can I jump? Down the line?
Yeah.
Yes. Okay, what about the one on the bottom? Jason's shaking his head no. Okay, no, it is not. There is not a common difference between them. Okay, there's no constant. Okay. Some more something else. Okay, now, something that's important to learn about these sequences that we'll address with our series too. And I know we're going kind of back and forth. It's important to be able to evaluate them together because they tie so closely together. So we go back and forth. If I have 6 terms, right? How many jumps am I going to have to get from one to the next? 5. If I have 3 terms, how many jumps do I have? 2. So something when we are going back to finding just the expression for finding the nth term. When it says find the nth term, it's just saying find the location of the 5th spot, or find the location of the 20th spot, or find the location of the 3rd spot, is all it's saying. These are our instructions. So I am finding the value at this certain location, A to N, A sub N. Whatever number this is, I'm going to find, so whatever my value is, I'm going to find the number that shows up at that spot. If I had a graph, I would be going there to find out where it's at on the graph, okay? We have this generic formula, and it says that I'm going to take wherever I'm starting, A sub 1, so here's my A sub 1. So to find any of these terms, I'm going to start at the beginning, and I'm going to add the jumps. Okay? And it's written as n minus 1 times d. D is our common difference. Remember, d is this value that we are jumping. Okay? I wanted you to see with this why it is written n minus 1. Because if I'm starting at 1 and I am trying to go to 9, how many of the same jumps is it going to take me to get there? 8. It's going to take me 8 jumps. So I'm going to have 8 of the exact same jumps added to the beginning. It's written in a formula as n minus 1. If we were to work that out, a sub n equals a sub 1 plus n minus 1d. Okay? So where I start plus a certain number of jumps, do we agree that if I had 1, 3, 5, 7, 9, and I'm going to the 5th term, that what I'm doing, we know this is 2 each time, that if I do 1, missed 1, 1 plus 8, I'm going to get to 9, because I have 4 sets of 2. That's what we're doing here. Okay? So as when we're adding, we're doing the same amount of jumps, so we're just doing multiples of it. Okay? Let's use our math rules, our distribution rules, and see what this turns into. A sub 1 plus d times n minus d. Okay? What this ends up working out, I didn't plan on it looking out like that, is our jumps, basically it's saying our jumps at the end and then we have to subtract off 1. Okay? What if we didn't start at 1? What if we started at 0? Could we find the 0 value if we know where we started and what our jumps is? Okay. What would our 0 value be for this? Because it has to be the same.
-1.
-1. Okay? when we start at 0, what we're going to see when we plug in real numbers is that when we start at 0 and we back this up, then our jumps actually become the real number of jumps that we had. If we're getting to 9, then our jumps are really 9, right? If I backed it up to 0. And I think I have one that shows the actual equation for it. But this, I use this one all the time. For me, logically, sometimes it's hard to just memorize a formula, but it's easier to logically think. If I start at the very first place and I'm trying to get to 9, I'm going to jump there 8 times to get to 9. So all I have to do is take what I started plus however many times I jumped and what my jump value is. Okay. So if we look at this rule, we've got 50, 44, 38. What is our common difference? What would be our D value? Other than it being written up there. What is our D? Negative 6. Okay, where are we starting?
1.
Okay, so a sub 1 is 1. Okay, so we can use it and say for any term, I know I have to start at 1. I'm going to jump by negative 6 a certain number of times. How many times am I going to jump? N minus 1. Right? So my generic equation for this one is a sub n means 1 plus negative 6n plus 6. Okay? So watch what happens when we did this. We have 7 minus 6n, or maybe negative 6n plus 7. We like to put our variable first. Okay. So now my equation is written with the exact same n values. If I have 10, if I'm trying to find number 10, I'm trying to find 10 jumps, because what I did is I backed up. So I'm starting at 56 and moving my way down. Right? So when we plug it in, we can see that if we are finding the value, we know that our first term for this case is 50. We're jumping 49 times. Right? Can I plug that as a 49? But if I was going 50 turns, I'm starting at 50. However many turns I'm going, I'm going to do one less than that times 6. So I've got 50. I use distribution, minus 6n plus 6. So if I really started at 56, if I started at my 0 value of 56, I would just jump negative 6 times however many times to get to that term. So if I'm finding the 20th term, I would have 20 jumps because I really started back at the 0. So that's when these two numbers get paired up and it's actually pushing you back to that a sub 0, this 0 location. You're like, where did the 56 come from? So you should notice that when you work this out, your first term will always be in sequence. It should match your sequence if you get another number up there. Okay? So what if you have, let me go back up. Okay. So we can write a rule for any sequence if we know one term and the common difference. Right? As long as they give me any term and I have my common difference, I can plug what I know. Remember, let's go all the way back to almost the first or second week. I said math is all about taking what you know and applying it to what you don't know. Right? So if I know any term, and I know the common difference, I can plug it in and I can get my whole answer. Because if I know a sub 1, if I know the first term and the common difference, I can find another value, right? But what if I don't have that? What if I actually know, in this case, a sub 13 equals 30? I could rewrite this and say a sub 13, all I'm doing is changing it. I don't know what my first term is. What is my n value? 13. Has to match. 13 minus 1. And they gave me my common difference of 3 halves. Okay. Then they say that a sub 13 is really 30. Okay. Now I have an equation with one variable. Can we solve an equation with one variable?
Yes.
Yeah. So now you solve for your first one. Then once you solve for it, could I go back and plug it into my generic one and get a whole generic one for this whole equation? No. I found out that a sub 1 is 12, so I could go back and rewrite it and plug in 12. For any unknown, what I did was actually distribute it out and then combine my first and last and write our generic equation. So we can go back and forth. We can always take what we know, apply it to what we don't know, use math to go back and forth. Okay, so what if they don't give you the common difference? What if they just give you 2 random terms? Okay. So they give us 2 different terms. In this case, it says a sub 6 equals 10 and a sub 21 equals 55. Well, let's plug it into the equations that we know. We know if a sub 6 is going to equal a sub 1 plus 5. Why did I just go ahead and write 5 there?
6 minus 1.
6 minus 1, perfect. So 5d, right? So now I have an equation, and I can rewrite it, right, as 55 equals a sub 1 plus, oh, this one, 10. So 10 equals a sub 1 plus 5d. But I have an equation that has 2 variables. Uh-oh, what do we know? Can we solve one equation for 2 variables? No. Can we solve 2 equations for 2 variables? Yes. Remember, we always have that. This is our substitution and elimination that we learned. We can always go back and we can solve multiple equations as long as we have the same number as the variables. So on this one, we're going to plug in a sub 21 equals a sub 1 plus 20. Why do I have 20? Why did I write 20?
Oh, because it's 21 minus 1.
21 minus 1. If I have 21 terms, I'm jumping 20 times d. We're going to simplify and plug it in and get 55 equals a sub 1 plus 20d. Okay. Now I've got 2 equations with 2 variables, so we can solve either by substitution or by elimination.